Welcome back, everyone. In this video, I will go over the article titled Avoiding Race Conditions in Shared Array Buffers with Atomics. This is an article written by Lynn Clark. It's on hacks.mozilla.com. I posted a link to this article. This is the final article in a series of 3 articles about memory management that Lynn wrote. This is the first time I'm reviewing this article. So I will be just going through this article and learning. If you could follow along with it, and if you find it useful, please let me know. Mostly it's for me. Anyway, in the previous article, shared buffers and array buffers were briefly explained, and then also a hint was given how a race condition could happen. So if you have a shared buffer and 2 web workers are writing to it at the same time, then there is a race condition. So this makes working with shared buffers really hard. So anyway, so the shared buffer feature was built, but they don't expect application developers to use shared array buffers directly. But library developers who have experience with multi-threaded programming in other languages can use these new low-level APIs to create higher-level tools. They expect there will be abstractions built on top of shared array buffers. There will be a library that most developers will end up using, a library that will simplify using this feature. So once the library is built, application developers can use these tools without touching shared array buffers or atomics directly. And they show a cartoon here which briefly talks about it. As you can see, this abstractions layer has JS libraries and also WebAssembly threading. So at least in the beginning, developers will end up using these JS libraries or WebAssembly threading to access the shared array buffer plus atomics feature to prevent race conditions, to handle race conditions better. So even though you probably shouldn't work with array buffers and atomics directly, I think it's still interesting to understand how they work. So in this article, I'll explain what kinds of race conditions concurrency can bring and how atomics help libraries avoid them. But first, what is a race condition? So they show a nice cartoon here. A cartoon, there are 2 web workers. I mean, the stickmans are nothing but the web workers. Both of them are trying to go access the memory at the same time. So there is a race condition. Race conditions, an example you may have seen before. A pretty straightforward example of a race condition can happen when you have a variable that is shared between 2 threads. Let's say one thread wants to load a file and the other thread checks whether it exists. They share a variable file exists to communicate. Initially, file exists is set to false. So they give an example here. In this example, there is a variable called file exists, which is set to false, and there is one web worker that is trying to set it to true, and the other web worker is trying to check if it is true, and if it is true, it wants to do something. As long as the code in thread 2 runs first, the file will be loaded. So they share a variable called file exists. So in this case, if web worker 2 or thread 2, the one on the right, if it executes first, then the code on the left will be able to load the file properly. So there is a race condition. If someone is trying to access the variable and someone is trying to set it at the same time, there is a race condition. But if the code in thread 1 runs first, then it will log an error to the user saying that the file does not exist. Yep. So because initially it's set to false, if code on the left side, if it is right now, if you see the cartoon here at the bottom of the screen, the left bottom of the screen, the cartoon, if you can see, if it is set to false, but there is one thread that's trying to set it to true and the other thread trying to check if it's true and then executing some code. If the left web worker gets to file exists first, then the web worker will not be able to load the file, even though the file might be available. So there is a race condition there. But yeah, but if the right side one executes first, you know that the left web worker will be able to load the file. But that's not the problem. It's not that the file doesn't exist. The real problem is the race condition. Many JavaScript developers have run into this kind of race condition, even in single-threaded code. You don't have to understand anything about multi-threading to see why this is a race. However, there are some kinds of race conditions which aren't possible in single-threaded code, but that can happen when you're programming with multiple threads and those threads share memory. So the race conditions happen in single-threaded code also, especially when you deal with asynchronous events. But you don't have to, in single-threaded code, you will not encounter, you won't encounter problems where memory is accessed. Especially if in multi-threaded applications, when you have multiple threads sharing the same memory. So different classes of race conditions and how atomics helps. Let's explore some of the different kinds of race conditions you can have in multi-threaded code and how atomics can help prevent them. This does not cover all possible race conditions, but should give you some idea why the API provides the methods that it does. Okay, they're going to talk about some examples of race conditions. Before we start, I want to say again, you shouldn't use atomics directly. Writing multi-threaded code is a known hard problem. Instead, you should use reliable libraries to work with shared memory in your multi-threaded code. Okay. Lynn recommends we still, even though they're giving some examples of atomics here, the recommendation is use a third-party library because writing multi-threaded code is a pretty hard problem. So with that out of the way, race conditions in a single operation. So let's say you had two threads that were incrementing the same variable. You might think that the end result would be the same regardless of which thread goes first. So here is an example. There is a shared variable. Both of them are incrementing it. So in most cases, if both of them are doing a simple increment, it shouldn't matter much which one goes first. So they're giving an example. In this case, if this one updated first and this one updated second, the shared variable is value 2. And in this case, if the right web worker updated it first and the left worker updated second, even then the variable is incremented to 2. But even though in the source code, incrementing a variable looks like a single operation, when you look at the compiled code, it's not a single operation. At the CPU level, incrementing a value takes 3 instructions. That's because the computer has both long-term memory and short-term memory. There's another article where they talk about short-term and long-term memory. So long-term memory typically referred to as RAM, and short-term memory is typically referred to as registers. And there is a ALU, a logical unit. So anyway, ALU is the one that uses the registers or the short-term memory. All of the threads share the long-term memory, but the short-term memory, the registers, are not shared between threads. The short-term memory is not shared between threads. Each thread needs to pull the value from memory into its short-term memory. After that, it can run the calculation on that value in short-term memory. Then it writes that value back from its short-term memory to long-term memory. So this is pretty important. So each thread, let's say there is a variable, it pulls the value from the long-term memory, typically RAM, and puts it in the short-term memory, and then runs some calculations, and then it stores the result back in the long-term memory. So they give a nice cartoon example here. So load the value from memory into register. So here the first cartoon here shows a long-term memory having a value 8. And from that 8, the value is loaded from the long-term memory to the short-term memory. And then the ALU, forget what ALU stands for, but let me check. Arithmetic logic unit. So anyway, the ALU runs calculation on the value and then puts the value back in short-term memory. Here the value got changed. Basically the value got incremented to 9, and then store the result to memory, and then the value is sent back to the long-term memory. If all of the operations in thread 1 happen first, and then all the operations in thread 2 happen, we will end up with the result that we want. They're saying if the operations happen sequentially, then we will end up with the result that we want. Here they're showing the increment. Let's say if the value is 8 and we are incrementing it. So the left thread or the left web worker, let's say it processes it first. It goes from 8 to 9, and then sequentially the right thread gets to process it. Then it increments it by one more, and the result value is 10. But if they are interleaved in time, the value that thread 2 has pulled into its register gets out of sync with the value in memory. This means that thread 2 doesn't take thread 1's calculation into consideration. Instead, it just clobbers the value that thread 1 wrote to memory with its own value. Because we can't guarantee, because there is a race condition, let's say both the calls are invoked exactly at the same time, and both of them get the value from the long-term memory at the same time, so that they step over each other. So the first one updates. If you see this cartoon, both of them took the value. I think if you see this one, the middle part of it is the long-term memory or RAM. Both of them pulled value 8 into their own registers, and then the left one incremented it, and the left one pushed it back into long-term memory, and then the right one also incremented its own register to 9 and then pushed it back. So this is not what we are expecting. We are expecting to see value 10 there, but we end up seeing 9. So this is a pretty good explanation. Thank you, Lynn. I think this is, I haven't gone through this in a long time. This is a very good refresher for me. One thing atomic operations do is take these operations that humans think of as being single operations, but which the computer sees as multiple operations, and makes the computer see them as a single operation too. So atomics takes the operations that humans think of single operations, even though they're multiple operations, and makes them look like single operations to humans, is what atomics will do. So this is why they're called atomic operations. It's because they take an operation that would normally have multiple instructions, where the instructions could be paused and resumed, and it makes it so that they all happen seemingly instantaneous, as if it were one instruction. It's like an indivisible atom. So they're called atomic operations because atomics takes these multiple instructions and they will make as if they are together, is what I'm getting. In other languages, you have something like mutex. So you can, there are a lot of features in other languages like C, which will allow you to lock the operation, and if there are two operations, let's say incrementing this shared variable, there is a way to lock, put a lock on that variable while one of them is processing. I don't know if in JavaScript or in atomics it's the same way. I think I will know I will know as I read through this, I think. So using atomic operations, the code for incrementing would look a little different. Okay, they're saying they're showing how to do it using atomics. Looks like if there is a shared variable and you want to perform a increment operation on a shared variable, you would use atomics, and you would use a method called add on atomics, and you would give it shared array buffer view. Shared array buffer view, as you can see in this cartoon, it's nothing but a view into a typed array, and the type is int8 array. So basically the array buffer here is split at the 8-bit mark. And you would say, what is the index? Let's say you want to update the 5th value in the array, then you would pass 4 in the index here. And then you would say, hey, how much do you want to add to that number? So it looks like we're adding 1. So that's how you would increment it. So now that we are using atomics.add, the different steps involved in incrementing the variable won't be mixed up between threads. Instead, one thread will finish its atomic operation and prevent the other one from starting. Then the other will start its own atomic operation. So a method like add in atomics will make sure that till it finishes an operation till it finishes its operation on that memory chunk, anything else that's trying to access will end up waiting. It will prevent the other thread from accessing the same chunk of memory. And once this is done, then the other one can. So basically the queue up. So let's say you have 2 add operations. So the first one that executes will block the second one. And after the first one is done doing the add operation, the second one can take over. And the second one can add it. So they demonstrate that in an example here. Here you can see, I think the sequence doesn't matter here. Either the left or the right web worker, whichever one gets to the whichever one, if the system executes the right one's atomics.add method, then it will lock that memory location, and then it will process that and then put it back, and then once it's done, the next one will take over. So atomics has a bunch of methods. The atomics methods that help avoid this kind of race are, so atomics has the following methods: add, subtract, I'm guessing its sub is subtract, and, or, XOR, and exchange. Okay. You'll notice that this list is fairly limited. It doesn't even include things like division and multiplication. A library developer could create atomic operations for other things though. Okay. So they're leaving it to library developers to add division, multiplication, and any other methods. So to do that, the developer would use atomics.compare exchange. With this, you get a value from the shared array buffer. Perform an operation on it and write it back to the shared array buffer if no other thread has updated it since you first checked. If another thread has updated it, then you can get that new value and try again. So they give an example. So you could use the compare exchange to get a value on the shared buffer and then perform some operations and then write it back. But before writing back, you can check, hey, has the value changed? If it's changed, then you can retry it. They provide more granular control also. So race conditions across multiple operations. So those atomic operations help avoid race conditions during single operations. But sometimes you want to change multiple values on an object using multiple operations and make sure no one else is making changes to the object at the same time. So that shows a single operation like a simple increment operation. An example for a simple, okay, so but sometimes you want to change multiple values, and it looks like sometimes you want to change multiple values on an object using multiple operations. And we want to make sure no one else is making changes to the object at the same time. Basically, this means that during every pass of changes to an object, that object is on lockdown and inaccessible to other threads. So if you start doing that, then that means every time we are changing an object, no one else can access it. The atomics object doesn't provide any tools to handle this directly, but it does provide tools that library authors can use to handle this. What library authors can create is a lock. Yeah. So in a lot of languages, you have lock. So if you're performing changes to multiple values and performing multiple operations there on them, so looks like atomics object doesn't provide any tools, but a library author can create a lock API that JavaScript users can use, JavaScript developers can use to lock a chunk of memory. Basically, you can lock multiple values. Now they're showing here, I think they logged 1, 2, 3, 4, 5 of them. So I don't know if there are libraries already that do this, but they're hoping third-party developers will end up developing those. If code wants to use locked data, it has to acquire the lock for the data. Then it can use the lock to lock out the other threads. Only it will be able to access or update the data while the lock is active. Okay. So looks like if your code wants to update the locked data, then you have to acquire a lock for the data that will lock out other threads from using it, and then you make updates to the data that you logged. To build a lock, library authors would use atomics.wait and atomics.wake, plus other ones such as atomics.compareExchange and atomics.store. So they give a few examples of what library authors can use. If you want to see how these would work, take a look at this basic lock implementation. So they have an example here. I don't know. Let me see. Okay. Oh. Someone wrote some code to show how locking can happen. So in this case, thread 2 would acquire the lock for the data and set the value of logged to true. So looks like they're showing this cartoon example. In the cartoon example, thread 2 would use a third-party library. In this case, as you can see, the stickman from thread 2 has come, and then they logged like two values or two variables. This means thread 1 can't access the data until thread 2 unlocks. Yeah, that's understandable. So if in this case thread 2 logged this data, so thread 1 won't be able to access it till thread 2 unlocks this data. If thread 1 needs to access the data, it will try to acquire the lock, but since the lock is already in use, it can't. The thread would then wait, so it would be blocked until the lock is available. Okay, so if thread 2 locked it and thread 1 wants access to the same data, it has to just wait. Once thread 2 is done, it would call unlock. The lock would notify one or more of the waiting threads that it's now available. Okay. So as soon as thread 2 unlocks it, so the unlocking mechanism will notify all the threads that are waiting for that data. So the thread could then scoop up the lock and lock up the data for its own use. Yeah, then in this case, thread 1 is going and locking the data, and it will use it for its own use. A lock library would use many different methods on the atomics object. But the methods that are most important for this use case are atomics wait and atomics wake. So for lock libraries, looks like the two most important methods are atomics.wait and atomics.wake. Race conditions caused by instruction reordering. There is a third synchronization problem that atomics take care of. This one can be surprising. You probably don't realize it, but there is a very good chance that the code you're writing isn't running in the order you expect it to. Both compilers and CPUs reorder code to make it run faster. For example, let's say you've written some code to calculate a total. You want to set a flag when the calculation is finished. To compile this, we need to decide which register to use for each variable. Then we translate the source code into instructions for the machine. So they gave a sample code here, subtotal, total is done. So to compile this, we need to decide which register to use for each variable. Then we can translate the source code into instructions for the machine. Okay. So here they're talking about storing it in a register. So that's saying add R1, R2, add R1 and R2 and store it in R3. Add R4 and R3 and store it in R4. Okay. R3 is nothing but subtotal here. R4 is nothing but total. And move 1 to R5. Basically, we are setting is done. Is done is nothing but R5, and we are moving 1 to is done. Yeah, they're showing what R1, R2, R3, R4, R5 represent. I think this is before any of the operations execute, they're showing what the values are. So far, Everything is as expected. What's not obvious, if you don't understand how computers work at the chip level, is that line 2 in our code needs to wait a little bit before it can execute. So line 2 in our code needs to wait a little before it can execute. Obviously, I'm guessing if they're talking about this line 2 total plus equals subtotal. It has to wait for the first operation to finish before you can execute the second one. Okay. Most computers break down the process of running an instruction into multiple steps. This makes sure all of the different parts of the CPU are busy at all times. So it makes the best use of the CPU. Okay. So looks like most computers break down the process of running instruction into multiple steps. So that way the CPU is optimally utilized. Here's one example of the steps an instruction goes through. So they have another cartoon example of what happens, what happens to an instruction, what are the steps an instruction goes through. Okay, so fetch the next instruction from memory. Fetch the next instruction from memory. So is this the first instruction? Okay, yeah, this is the stage 1 they're talking about. So this is an example of all the steps that an instruction goes through. So the first step is it'll fetch the next instructions from memory, figure out what the instruction is telling us to do. Decode the instruction and get the values from the registers. So it gets the instruction and then it figures out, it decodes the, so if it says add R1, R2 and store it in R3, it needs to decode it. So it needs to basically get R1 from the register and R2 from the register and perform a calculation. The ALU will perform a calculation on that. So execute the instruction. Let's see. So the third step is it'll execute the instruction. Looks like that'll be done by the ALU. And stage 4 will be write back the result. So stage 4 is writing it back, writing the result back. So looks like a small instruction, like if we go back here, if you take the first line, subtotal equals price plus fee, that will translate to add R1, R2 and store it in R3. And that's the first step. It'll fetch that instruction. And the second stage is decode it. Basically, what is R1, what kind of operation it needs to perform, and what kind of operation it needs to perform, and on what values does it need to perform this operation is the second stage. It'll decode and fetch the register values. And the third one is it'll execute that operation. That will happen in the ALU. And then the fourth stage is write back the result to the register. So that's how one instruction goes through the pipeline. Ideally, we want to have the second instruction following directly after it. As soon as it has moved into stage 2, we want to fetch the next instruction. The problem is that there is a dependency between instruction 1 and instruction 2. Yeah, as we've seen before, there is a dependency between these two. I think the second instruction depends on subtotal. We could just pause the CPU until instruction 1 has updated subtotal in the register, but that would slow things down. To make things more efficient, what a lot of compilers and CPUs will do is reorder the code. They will look for other instructions which don't use subtotal or total and move those in between those two lines. So it looks like they will reorder the instructions for you. In this case, is done has nothing to do with subtotal and total. So it looks like if we move is done to the second line, so is done, because there are no dependencies, the compiler or CPUs can run the second instruction. So that way the CPU is kept busy. I mean, it's optimally utilized. So this keeps a steady stream of instructions moving through the pipeline. Because line 3 didn't depend on any values in line 1 or 2, the compiler or CPU figures it's safe to reorder like this. When you're running in a single thread, no other code will even see these values until the whole function is done anyway. But when you have another thread running at the same time on another processor, that's not the case. So in multi-processed applications, it will be a problem. The other thread doesn't have to wait until the function is done to see these changes. It can see them almost as soon as they're written back to memory. So what they're saying is, even though we are not done, if you are in a multi-threaded application, if is done, if the compiler or CPU ends up executing is done equals true, even though it's not done, the other thread might, if the other thread is also looking at this variable for whatever reason, it could assume that, hey, it's already done, and it could start something else because is done is true, and we might end up having inconsistent results. Yeah, that's what they're talking about. The other thread doesn't have to wait until the function is done to see these changes. It can see them almost as soon as they're written back to memory. So it can tell that is done was set before total. If you were using is done as a flag, the total had been calculated and was ready to use in the other thread, then this kind of reordering would create race conditions. Atomics attempts to solve these bugs. When you use an atomic write, it's like putting a fence between two parts of your code. Atomic operations aren't reordered relative to each other, and other operations aren't moved around. In particular, two operations that are often used to enforce ordering are atomics load and atomics.store. All variable updates above atomics.store in the function source code are guaranteed to be done before atomics.store is done writing its value back to memory. Okay. Even if the non-atomic instructions are reordered relative to each other, none of them will be moved below a call to atomic store, which comes below in the source code. Okay. And all variable loads after atomics.load in a function are guaranteed to be done after atomics.load fetches its value. Again, even if the non-atomic instructions are reordered, none of them will be moved above atomics.load that comes above them in the source code. Okay. So they're showing an example of how to make sure the CPU or compiler doesn't reorder instructions. So in this case, there are again two threads, or for example, in JavaScript, two web workers maybe. So here they're saying variable updates above atomic store are guaranteed to be done before atomics.store completes. Okay. So when we have something like this, atomics.store view1, so the instructions above atomics.store are guaranteed to complete before we execute atomic.store. So any variables, and if you have atomics.load, any variables below atomics.load are guaranteed to be done after atomics.load finishes whatever work it needs to do. So these two can help make sure that the CPU or compilers don't reorder instructions. The while loop I show here is called a spin log. And okay, here we're talking about. So note the while loop I show here is called a spin log, and it's very inefficient. And if it's on the main thread, it can bring your application to a halt. You almost certainly don't want to use that in real code. Once again, these methods aren't really meant for direct use in application code. Instead, libraries would use them to create logs. So in conclusion, programming multiple threads that share memory is hard. There are many different kinds of race conditions just waiting to trip you up. This is why you don't want to use shared array buffers and atomics in your application code directly. Instead, you should depend on proven libraries by developers who are experienced with multi-threading and who have spent time studying the memory model. It is still early days for shared array buffer and atomics. Those libraries haven't been created yet. But these new APIs provide the basic foundation to build on top of it. So at a high level, they're saying, okay, do not, these are shared array buffer is not ready for prime time. We should be using it. We should be using an abstraction, or in this case, make sure use a library that's built on top of atomics library, the atomics methods, and shared libraries to do, yeah, to use shared memory. Cool. That's all I have for this video. I think this is a pretty awesome series. I mean, I learned a lot. Hopefully, whoever is reading or viewing this video learned some. Feel free to go to these articles, and if my way of presenting this is not good enough, please go to these articles and you'll be able to learn it firsthand from Lynn. Thank you very much, and I'm going to stop this video now.